Hello everybody, welcome to my video on tangent lines, generally the last video of the circles unit for me. There's really two things you need to know about a tangent line other than what a tangent line actually is. And what it is, it's a line that passes by a circle, touching it only once. The point of tangency is D. First thing you'll need to know is that when it intercepts a radius or a diameter, it's automatically going to make a right angle. And I will show you the other thing on this slide. So usually I will have a student come up and put a point anywhere outside the circle. So maybe a student comes up and puts a point about here. So again, what a tangent line is, it's a line segment that will go from that point to anywhere to the point where, again, it's going to intercept the circle one time. Apologies, I was having a little bit of trouble with the mouse there. So it looks like it would touch about right there if it was going to pass by the circle one time. Now I can make two of these line segments to each circle coming from any point. So again, I'm kind of looking for the place where it's only going to touch one time. And that second thing you need to know is that as long as these two tangents are coming from the same point, I'm going to call it P, these are automatically going to be congruent or equal to each other. So if I measured that on my screen, it might measure about, I don't know, maybe 20 centimeters. So then this one should measure the same 20 centimeters. And then again, remember, wherever they touch a radius, they're going to make a right angle. Well, let me do that properly. Wherever they touch a radius, they make a right angle. Same thing with the other one. Wherever it touches a radius, right angle. So those are two things you need to know. Now let's check them out in terms of some problems. Starting with number 16 down here. So I've got an X over here, I've got a 9, I've got an 8 that appears to only be representing this space, but all the radiuses, all the radii are the same in any circle, so this one is guaranteed to be 9. So the right angle is guaranteed to be here because tangents and radii make right angles. So the hypotenuse is this 17 over here. So to find x, I could use Pythagorean theorem, a squared plus b squared equals c squared. That would be the x and the 9 both squared and the 17 squared. 17 squared is made 289. 9 squared was 81. Subtract the 81 to get down to 208 and get rid of a square by square root. So whatever the square root of 208 is, would be x. Meanwhile, again, tangent lines and radii make 90-degree angles. So this time I've got a squared, a b squared, and a c squared. That's the hypotenuse over there. So I'm going to put x squared at the end. 13 squared to begin with, and 16 squared. And do you know where I got 16 at? This 8 being centralized up here would represent just that radius. So the bottom radius must be 8 as well for a total of 16. Square both of those, add them together, and get rid of the square by square rooting, whatever they come up to. I squared them both. That was 169, 256. Add them together is 425. And again, I got rid of the square by square rooting. Next up, got a 24, got a 7, and we're missing the whole hypotenuse over here. Now, note it appears that we're looking for the x and the y over here and how that breaks down. Well, first of all radii are the same in any circle, so y is going to be 7. All radii are congruent or equal within the same circle. So 7 squared plus, and the right angle is always the tangent and the radius, so my other leg must be 24. And then finally we're going to look for, you can call it z for the whole thing, or you can call it x plus 7. Kind of easiest to call it z. Just don't make sure your z doesn't look like a 2. A squared plus b squared equals c squared. It's going to come up to 25. Now, how exactly do I know that? So I actually know that because teaching geometry a lot, I'm very familiar with what's called Pythagorean triples. There's not very many combinations of right triangles in the world. The most popular one, 3, 4, 5, I should say combinations of whole number right triangles. If I double 3, 4, 5, 6, 8, 10 is another popular one. 7, 24, 25 is the one we were just using. There's a 7, there was a 24, so I know the other one had to be 25. 5, 12, 13 is also a very common one. I'd say this one is first most common. This one is second. The one we just had was third. Occasionally, I'll see this one occasionally, but I don't usually see the other ones. And there's more as you go to bigger numbers. And of course, you could have some that are decimals, but they wouldn't be called Pythagorean triples. Next up, find the value of x here. X is just this part. You can call the whole side W if you want to. And remember, we just found this whole side to be 25 and this was 7. So x had to be 18. 18 and 7 is 25. So sorry about that. Back on this one, I know the tangent and radius make a right angle. So let's say 8 squared plus w squared equals 17 squared. Oh, look, that looks like another one from that page. I believe it came up to 15 when you have that. 17 squared, subtract whatever 8 squared is. Make sure you square them before you subtract them. Get rid of the square by square rooting. W is 15, and that 15 must break down to 7.5 and 7.5. Now, I've made an edit recently in my flip book for this next question because there was just way too much Pythagorean theorem practice without emphasizing there's a whole nother use of Pythagorean theorem that I'm going to show you here. So is this really a tangent line? Well, if they make a right angle, that's a good indicator that this is a tangent line. And by the way, that's the 4 radius, and the 1 is just representing this part. So the other rest of it must be 4 because it's radius, and all radii are the same in the same circle. So anyways, if you check Pythagorean theorem, that would be 3 squared plus 4 squared equals the hypotenuse, which is 5 squared. And you might recognize, I just emphasized 3, 4, 5 is a right triangle. If I square 5 squared, that's 25. This is 16. This is 9. And 25 does indeed add up to 25. So long story short, you can use Pythagorean theorem to check and see if 3 sides form a right triangle. If I would have got something like 27 is equal to 25, then that would be no. They were close. So it'd be close to a 90-degree angle there, but to be tangent, it's got to be 90. So now remember, there's 2 things you need to know about tangents, and we just really over-exhausted the fact that they form 90-degree angles. The other fact was that when they come from the same location, when they originate in the same place, they're automatically going to be equal to each other. So how do you solve that? Well, we've done a lot like this. They're equal to each other. Subtract 3x to move the smaller one is 5x, and I want to stay balanced, so I'm going to move minus 39 over here, and it'll become plus 39. I basically added 39 to both sides, giving me 55. Divide off the 5, and x is 11. So 3 times 11 is 33 plus 16. This piece must be 49, so the other piece must be 49. They're guaranteed to be the same. And I wasn't necessarily asked to do that. The question just wanted x. So we could have stopped at that point, but it was worth showing. And then finally, very similar question. We're looking for the perimeter, it says up here, of the whole triangle. The best piece of information we have is this 7 that's tangent, and this one is tangent, both coming from the same place. So they're both 7. And if this whole side is 26, then this tangent must be 19. And these 2 tangents are originating both from J. So it must also be 19. We don't know how long these pieces are. So what we can do again, we know that they are equal to each other. 4x plus 15 is equal to 15x minus 7. Subtract the 4x. Remember, easier to move the smaller one. Let's move -7 over to that side so we can stay balanced. I got my constants on one side, I got my variable on one side, and we get rid of a times 11 by divided by 11. X is 2. Now that doesn't mean these segments are 2, it means X is 2. And when I plug that in, I would get 23. Automatically, I'm going to get 23 for that one. Plug it in if you'd like to. Remember, we're looking for the perimeter. 7 plus 7 plus 19 plus 19 plus 23 plus 23. And I believe that comes up to 98 for the perimeter. One last question. I didn't use this one in class. This was from a released version of the EOC. And the figure shows concentric circles, meaning they share a center, and that center is 0. We got a chord that's tangent to the smaller circle, touching it one time. So remember what we learned. We're automatically going to have a 90-degree angle at the radius. The radius of the larger circle is 15. The radius of the smaller circle is 12. So the radius of the smaller circle being 12, I know that this is 12.
Attention students, please be quiet and listen to the following bus announcement.
The radius of the larger circle is 15, so I sketched a radius here. That's the whole circle, or the larger circle, to go with the radius of the smaller circle. The reason I made it into a right triangle is because right triangles are often lifesavers, especially when you have a 90-degree angle that you can use. So I'm looking for this piece. I'll call it W. Or I can find W. W squared plus 12 squared equals 15 squared. This looks like a 3, 4, 5. This is the 4, this is the 5, this is the 3, and they're all times 3. So which means this one must be 9. Finish Pythagorean theorem if you want to now. W is 9 there, which means this side is also 9. For a total, the question was asking how long is chord XY? That's 9 plus 9 for 18. And thankfully, they didn't use 9 as an answer choice. The answer choice D was 10 down there. So pretty good question there. Well, as always, thank you for checking out Tangents. The assignment for this is usually not a delta. It's usually a Quizizz code.